Right, good afternoon, everybody. This is a presentation about Synaptics' innovative distributed sensing technology. My name's Saul Matthews, and I'm the Commercial Director at Synaptic, and I'm going to be talking you through what we're doing in offshore wind to enable reduced operational costs by optimizing scheduled maintenance and automating the condition monitoring of remote assets in a wind farm. Now, very quickly about Synaptics, so you know who we are. We've invented a new category of instrumentation called distributed electromechanical sensing, or DES. What this means is that we're able to deploy very wide area, very long range sensor networks, and these sensors are completely passive. That means you can instrument more remote or inaccessible locations faster and safer and more securely, because our sensors do not need power supplies, communications equipment, data networks, or any kind of time synchronization equipment, which makes it ideal for reaching very far away offshore and monitoring electrical systems such as wind turbines and cables. It's actually already deployed in transmission, so this is a transmission grade remote protection and condition monitoring system, which is actually all operating on one platform. So it was designed to do protection and metering applications in transmission, but it also works to automate condition monitoring and improve asset management data insights for operational purposes. Now, I have to quickly explain what that technology platform is. So think of this as two components. We have an interrogator unit in a substation somewhere. It could be onshore or offshore, which is connected by optical fiber, which is already available in the power cables in the network, to reach out and deploy lots of sensors. And we're using that fiber as a network, not as a microphone. This is not DTS or DAS. This is electrical and mechanical sensing, which is using the fiber to bring the signal back very quickly and very fast. In fact, we use standard industry standard current transformers and voltage transducers, CTs and BTs that you'd see in any substation around the world, but we figured out how to make them passive, and they connect through the fiber, so it's very easy and safe to retrofit them. And it means at any location that you want to measure something, there's no data, there's no latency, there's no wireless signal, there's no maintenance of batteries or equipment, because there's no power. In fact, there is no data outside your substation, so it's faster, longer range, and more reliable than any existing technology. And we can measure any combination of voltage, current, strain, vibration, or temperature up to 100 kilometers away from the first sensor to the last at the speed of light through that fiber. And that's important for offshore wind, because effectively this combination of all these different parameters are brought in live into this box, only connected by light through the fiber. And that means we've got instantaneous live representations and visualizations and correlations of what's happening out there back in the control center. And that can be used in three different ways. And we normally talk about this across three different time scales. So when we're thinking about protection applications, we're operating within 2 milliseconds to find a fault, isolate it, and get back into production as fast as possible. So at a very simple level, our technology is used for digital substations around the world where you want to limit the cost of an outage. And it's about automatically reclosing around a faulted cable in an array, and then keeping production up as high as possible and keeping outage as low as possible. But while there's not a fault and these sensors are out there recording everything that's happening, it's also very good for enhanced real-time control functions. That's in human timescales of seconds and minutes, where we're looking for things like overheating terminations and setting alarms that can warn people of a problem that's about to happen to prevent catastrophic damage before it gets too big of a problem. And also that enables real-time thermal rating, which I'll get onto in a moment. But when you take all of that data and you store it and you build a history over time, you can trend line that data, and you get into the world of prognostics that says there is a way to reduce scheduled maintenance because our sensors are so sensitive that we're picking up clues about impending failures of individual components in the electrical system. And that means we're spotting faults before they happen and warning of when it's appropriate to go and do advanced replacements, and also eliminating sources of cable damage, which is still the industry's biggest cost factor and probably the hardest thing to predict or control. So for all these reasons, this technology can play a role. But let me explain this in a bit more detail for you. So we've been working with the Offshore Renewable Energy Catapult at Leavenworth to do our first offshore wind demonstration, where we instrumented array cables. So in a typical string of up to 8 cables, we can instrument all of them with one system, and you're basically upgrading from a distance protection scheme to a multi-zone unit protection scheme. So if there's a fault in an individual cable, we can isolate that cable, reclose on all of the other cables and turbines and keep them in production, limiting the fault and limiting the outage time while repairs are scheduled. Now, that's particularly useful if you're economically, if that's a scheme that's using cables bigger than 66 kV, which is going to be the norm in the future, and where operators are now considering putting switchgear in the turbines, because especially for floating wind, that means you're going to be able to do delayed auto reclose, and you can hot swap floating turbines in and out of a circular array without disturbing the protection scheme and causing a false trip and a total outage. So it's going to be a critical enabler as wind farms get bigger and cables get longer and carry more economic value. Now, we also talked about real-time control in the same system. So once you've installed the sensors, which you'll have noticed we could retrofit a cable in a day, we're also able to, and we've shown here with OREC, that we've also put temperature sensors on the terminations themselves. This is a critical failure point, and failures are quite common. There are multiple causes of why the terminators overheat, but they do, and some of them can fail critically. And this is not monitored by DTS. DTS can't see these locations, so this is complementary to DTS and provides additional insight and visibility to the scheme. They're very sensitive, and you can easily set a threshold alarm and send a goose message to warn of a problem. And because you can combine temperature monitoring and current monitoring or voltage monitoring at the same time, it means you can get to the goal of safely realizing the potential capacity of these cables, because if you've got live temperature and current correlations, you've got instantaneous control of how much current and load that system can take at any given time in real time. And real-time thermal rating, or what some people call dynamic line rating, is clearly something that's going to be of value in the future. And now, for these reasons, Vattenfall have also seen what we did at Leavenworth and asked us to install our first system at scale on one of their live wind farms, looking at instrumenting export cables. That's happening this quarter, and they're interested in something else which goes towards asset management and improved scheduled maintenance. That's monitoring power quality. If you don't know what power quality is, it's simply an electrical signal or power that you've generated but you can't sell because there's some kind of a loss. And every harmonic around the fundamental 50 Hertz signal, could be at 150 Hertz, which is the third harmonic, or up and up and up from that, is a particular loss from a specific source. If you can measure it, you can do something about it. So the third harmonic here, for example, is typically associated with thermal loss, like an overheating transformer, which we often instrument in digital power stations, but it could also be that overheating cable again. It's claimed in the academic literature that the 5th and 7th harmonic, if they're very prevalent in a place, that's probably a critical cause of premature cable aging, which in itself all leads to partial discharge and overheating, and it's a particularly pronounced problem with direct drive turbines. So power quality really matters because it's a fundamental source of the problem. So you'd think everyone monitors it, and they do today, but power quality is only monitored from time to time. It's not permanent, and it's only monitored at the output of an entire wind farm. So you get a net score of the effect of bad or good injections of power quality from every single wind turbine. That's good for grid compliance, but it doesn't tell you the origin of a problem or any particular turbine that's misbehaving. So the goal here is to say, let's enable permanent and streaming power quality data. Let's read out the injection from every single wind turbine in the array, because we can, because we've got a very big sensor budget and long range, we can instrument that now. And then from this, you can get this timestamp data history built up for prognostics purposes. In a nutshell, what we're saying is you can spot a change in the harmonic profile from a turbine, which tells you of an impending component failure. That could be a converter or a filter or a bearing. You can compare like for like assets and say, why are these other 40 turbines behaving the same and have one signature and then the 50th one doesn't? That means you know to go and visit that one because something's about to go wrong, and that means you optimize your scheduled maintenance regime, and that's going to improve costs and anticipate failures with reduced outage. And finally, it means you can locate the origin of poor power quality injections within a string, and if you know the source of the problem, you can engineer a fix. And if you don't have the problem of power quality, it doesn't cause overheating and it does not cause partial discharge later on in life to damage the long-term viability of the asset. So if that makes sense, we'd love to come and have a deeper conversation with you. We are on the stand hosted by the Offshore Renewable Energy Catapult during this event, and we'd like to talk to you about the scalable control system of passive sensor networks, about how we can repeatedly, safely and reliably retrofit these to any existing array, and how we can give you new visibility of termination overheating and power quality insights that will reduce operations and maintenance cost by optimizing scheduled maintenance visits and automating as much as possible. Thank you very much.